listen to the silence of space. Tonight, we will fall asleep to stories about the space station and those who work there. Just close your eyes and let the voices from NASA take you to the stars.
Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 27, The Search for Life. I'm Gary Jordan, and I'll be your host today. So this is the podcast where we bring in the experts, NASA scientists, engineers, astronauts, all to tell you the coolest information about NASA and about space. So today, we're talking about something super cool, how we're looking for life in the universe. We're talking with Aaron Burton and Mark Fries. Aaron and Mark are both planetary scientists here at the NASA Johnson Space Center in Houston, Texas. And we had a great discussion about the different NASA initiatives, all looking at organic material in the solar system, and what we're finding from these studies that help us understand the fundamentals of life here on Earth and possibly in the universe. So with no further delay, let's go light speed and jump right ahead to our talk with Dr. Aaron Burton and Dr. Mark Fries. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit lights are correct. There she goes.
Houston, we have a podcast.
Well, this one's going to be good because I'm excited because this one's about the ultimate question, right? Are we alone in the universe? That's literally, it's in the NASA mission statement, right? Everything we do is to explore the unknown and or reveal the unknown for the benefit of humankind or something like that. So I guess I'll start off with this question. How many times a day do you ask yourself that question? Are we alone?
Well, it's back there, squirrel caging around somewhere all the time. I don't know if I stop in the middle of shaving and go, wait a minute, but are we alone? But, I do think about it on a regular basis. Sure.
I figure, well, because that's the whole thing, right? This is your job. Your job is to look for organic material, right? So I guess to just pull back, and I just think that would be super cool. Are we alone? Or, that's not bad.
Yeah, I think about it more at night. When you look up at the stars and you just see all of the stars, and that's just what we can see.
Yeah, exactly.
So the thought that we're the only game in town seems pretty unlikely.
I just took a camping trip out to Big Bend a couple weeks ago, and that was just an eye-opener because I thought I had seen, wow, there's a lot of stars in the sky, when I was living in Pennsylvania, but out in Big Bend, you can see the Milky Way, and there's constellations where you couldn't even see them because there were just that many more stars. It was just the clearest sky I've ever seen in my life. And I was like, wow, this is just, just a different part of Earth I can see this many stars. It was crazy. All right, well, so let's start off with just a little bit about you guys. And since you're both planetary scientists, kind of what your focuses are.
Okay. So I have built a research lab where we look for organic molecules that we find in meteorites. Mm-hmm. So these are carbon-containing molecules, and I'm interested in the ones that are related to biology, so things that biology could use. And so by looking at the organic molecules that are found in meteorites, it gives us a way to look at samples where biologically interesting molecules are made, but they weren't made by life. They were just made by sort of abiotic chemistry, things that can happen in our solar system. And so I'm interested in doing that because I want to know about the chemistry that was going on before life started. And then from understanding that chemistry, try and take the next step forward to think of, if we know the chemistry that was going on without life, how did that transition into a living system that we have?
Wow, literally the origins of life.
Yeah.
That's pretty cool. How about you, Mark?
I work in curation. I'm a scientist in curation. And then curation, I should explain it. We basically take care of NASA's collections. We have the Apollo moon rock collection. We have meteorites from Antarctica. We have samples from delivered by a couple of sample return missions. And all the curators, all the curation scientists are expected to have a scientific interests as well and maintain a scientific course of study. What I study is carbon in geological systems, not necessarily just organic chemistry. Aaron's much more of a specialist in that, much more of an expert in that than I am per se, but more of carbon in entire systems ranging from gas phase, carbon that you find in rocks, whether it's biological or geological, carbon as part of a system on planetary surfaces and interiors and such.
But it's fair to say, carbon is an essential component of life, right?
As far as we know, yes.
That's true. Yeah, there's a bunch of other things, that we can talk about. I don't know if you guys actually discuss silicon-based life forms or anything like that, or mostly carbon. Carbon's usually the good stuff, right? That's the basic form of life.
Yeah, well, so at the most simple, aspect, you have carbon, and we like it because it makes 4 bonds, and so you can make these long polymers out of it. And so if you just go down the periodic table, silicon, well, that does, similar things.
Right.
But carbon's actually pretty special. So if you compare carbon and silane, or methane and silane, so methane is CH4, silane is SiH4. Those would be sort of the analogous molecules, but silane actually is like an incredibly explosive gas, and it's very difficult to keep on Earth. Whereas methane, sort of hangs around and gets produced. So that works out well for organisms that produce methane and for life. And then if you start looking at other things like CO2 as a gas, that's what we breathe in and breathe out. Trees use that for photosynthesis. Mm-hmm. If you compare that to SiO2, that's
a rock.
Yeah, that's
kind of hard to breathe rock.
Yeah, so it's hard to breathe. It's not very easy for organisms to process it or to access it, and so it ends up being just a less mobile, sort of building block. If your whole life was centered around silicon, now it's all sand, right?
Oh yeah, a little harder. So carbon is just the magic ingredient, really, just because of that ability to bond to so many things.
At least based on physics in our solar system.
Well, so the whole just concept of life, searching for life, right? I mean, there's a lot of things that we study out in the universe, but this quest to find life outside the solar system, why is that so fundamental to us as humans to go out and to search for?
It's a good question. It's kind of hard to answer because it's just kind of the best answer I could give is that it's just a fundamental question. I mean, anybody who's looked up at night, like Aaron said, has had to wonder. I mean, there's an awful lot of stuff up there. Surely there's got to be something else. It's just a basic, almost primal, human query. I don't know how to put it any better than that, honestly.
Yeah.
Yeah, I mean, I think it's kind of like the human tradition of exploring, and first it started out, humans on a landmass, and they said, well, what's on the other side? What's over those mountains?
Right. What's
across that river? And then it expanded to what's across that ocean, and then what's at the bottom of the seafloor, and now what's on the next world's over, and it's kind of that exploring, but also then, if we're asking these questions, is there anyone else out there that's asking those same questions?
Yeah, that's true. I mean, if you think about human history, just the fact that people travel, they find a new civilization and can open up new trade routes, or even as far as cross the Atlantic Ocean and discover a whole new world, trying to find more trade routes or something like that. So it's just, I guess you're right. It's kind of built into our DNA that we just have this drive to it's not enough, right? We want to know. We want to know why. We want to know more.
You look at the sky, you say, I'm pretty sure there's life out there, but I want to sort of prove it,
Yeah.
I want to find it. Actually, no.
Pretty sure it's not good enough.
Luckily, humans have a low fascination threshold.
So I mean, just besides the fascination of it, why is it important to understand the origins of life? What can we get out of it?
Well, for me, I've just been interested, I guess, from the scientific standpoint of, how did life start? Which I think naturally leads to, could life exist elsewhere? And so those are two kind of the basic questions, because if life could exist elsewhere, then that answers your sort of fundamental intrinsic question of, is there life elsewhere? If you know how it started, then you know what signs to look for, what kinds of environments you need to look in, what types of chemistry needs to be going on for you to look there for life.
So how does just once you do that, I guess you can help you search for life outside. But what about here on Earth? Is there applications for once learning more about how the origins of life and how that comes to be? How can that help us here?
Let's see. I would answer that by saying that fundamentally we're answering. It's like we said, like talked about just a minute ago. This, understanding the origin of life is one of the primal, fundamental human queries that most people want to know. And as scientists, what our purpose is to discover exactly that sort of thing, to try to answer those sort of questions, to be the interpreters of the world around us, to try to enrich everyone's lives. And that's a really important thing that a lot of people are interested in. So it's a high priority for scientific investigation. For a more nuts and bolts approach, maybe understanding the fundamentals of how life arose would give us better understanding into our own biochemistry at a very fundamental level. That's a possibility.
Improving life for us, making life better for humans. Just however, bring it into industry, make better drugs, or understand how people grow up or develop, or how just life, right?
Right. The fundamentals of how a cell functions on the chemical level. It can't be bad to know more about that.
Well,
I would.
go ahead.
Sorry. So I would just add that a lot of what origins of life researchers try to do is sort of recreate how life could have started. Ideally, if you had a time machine, you would just go back in time, 4.5 billion years.
Oh, that'd be easy.
To the start of life. But it raises a philosophical issue, which is what if you disrupted that process, and so you actually killed life? So maybe that's a bad idea. But without a time machine, we don't have to worry about that. But the best we can hope to do is sort of recreate how life started, or how life could have started. And so a lot of the experiments that have gone on there have looked at, sort of alternatives to DNA. And so these alternatives to DNA have actually been shown to not be recognized by sort of modern biology. So you can make sort of a drug out of this alternative DNA that now has a longer lifespan inside of a human. And so it's kind of expanded the range of drugs that are accessible, and kind of opened up or helped contribute to the field of synthetic biology, where we can start, doing gene manipulation, genetic therapies. So there really are practical applications of it.
Yeah.
In addition to, satisfying our kind of curiosity about how life started.
Just, out of curiosity, these studies, are there any going on the International Space Station right now that have to do with sort of understanding life and how the origins, or maybe just how it affects humans?
Well, yeah, every astronaut that we send up there is sort of an experiment on how,
there you go.
how environmental conditions are affecting life and biology. But there's also exposures. So they put microorganisms on the outside of the ISS, for example, and then expose them to radiation, that sort of thing, bring the organisms back. So that's kind of an emerging field too.
All right, so we talked a lot about the why of why search for life and all of that, but let's pull back and just kind of understand just what we're talking about here. So how, as one of the experts in the field of understanding life and studying life, how would you define life, Aaron?
That's a good question that people have actually really wrestled with. It's not an easy one to answer. So the origins of life community has settled on a sort of mouthful, which is that life is a self-sustaining chemical system that is capable of Darwinian evolution. And so, there's a lot in there.
Yeah.
But self-sustaining means something that can actually, reproduce itself and grow, not necessarily grow in size, but grow in population. So if you have one molecule, now it can make, 10 more, et cetera, and continue to reproduce. But it's also important that it be able to actually change over time. And that's where the Darwinian evolution comes in. So if you have, a salt crystal that's made up of sodium and chloride, and you can add more sodium and chloride to that salt crystal, and it's getting bigger, so it's growing in some sense. There are more sodiums and chlorides in there, but it doesn't really change. right? So we would never call a salt crystal alive, even though it can, grow. It's a chemical system. So you really need that capacity to change for an organism to be able to do something different and to sort of respond to its environment. That's very technical.
No, it makes sense, right? You gotta check those boxes because otherwise, if you do the wrong definition, salt is life now. So
yeah,
you'll get that salt life sticker on the back of your car.
Yeah, well,
totally different thing.
Funny.
Yeah, it's awesome.
So then, how for you, Mark? I guess you're studying carbon specifically, right? So then, how does that fit into the picture of understanding life?
It kind of goes to what Aaron was saying about understanding the chemical conditions at the origin of life. There's a fun conundrum there, actually, in that, okay, we know that life arose on Earth, but it's basically being able to get directly at the conditions where that happened is very, very difficult because of, ironically, life itself. Life has basically overprinted everything on the planet. Whatever conditions it was that gave rise to life on Earth, they might be here today. They might be something at the deep ocean. There's all manner of hypotheses about this. But it's very, very difficult to pin that down because life has altered this planet so completely. I mean, from the mantle to the surface to the top of the atmosphere, chemically, morphologically, isotopically, everything has been changed. And so trying to get back at that original set of conditions that gave rise to life is actually really difficult here on Earth.
Wow. Is it postulated more that life itself started on Earth and then just sort of spread and literally changed the makeup of the Earth? Or is there some chance that maybe, it came from somewhere else and maybe just got delivered to Earth or something?
I don't like that. Here's the reason why I don't like that. Is the notion of life coming somewhere else is just from the standpoint that it doesn't actually answer the question of how life arose. You've just moved it somewhere else and put a almost impossible journey in between the origin and its evolution on Earth. We know that the Earth has been changed considerably by life. We have oxygen in our atmosphere because of it. I guess that's off on a tangent a bit, but yeah.
Please go if you need to.
So fundamentally, that's my problem with saying that it started somewhere else and came here, because that you are introducing a big complication to it without really putting any light on how it happened.
Yeah.
Yeah, as Mark was saying, we think life started in water on a rocky body somewhere. So whether that's Earth or Mars or somewhere else, you still need life to start on a rocky body with water somewhere. So speculating that it was Mars and then it got transported here doesn't, from a practical standpoint, doesn't help you address those conditions necessarily any better.
Well, still, I mean, narrowing it down to, we could say you need a rocky body with water for it to at least start, right? Is that at least a starting point for understanding the origins of life?
I think it is. That's a good distillation. There's another interesting little conundrum in there. Aaron mentioned Mars. And I was just talking about how Earth has been completely overprinted.
Yeah.
There's a lot of effort, a lot of interest in trying to find life on Mars, and that's fine, that's good. But there's kind of a hidden value to a completely dead Mars. Let me go off on a little bit of a tangent here.
Please do.
Let's say that life started on Earth and that Mars, even though it had all the conditions for life, apparently water, fairly warm, fairly dense atmosphere, never had life. If that's the case, then basically Mars has preserved in a kind of mummified state those conditions early in the formation of the terrestrial planets when life arose on Earth. So one of the fun conundrums here is that a completely dead Mars with no history of life may be a very powerful tool to understanding the origin of life on Earth.
Huh. So that's where the many rovers that we've sent to Mars over the year come into play, right? But we're studying Mars and trying to understand its history to see what we can learn about its past and see if what you're saying is true. Maybe the atmosphere was thicker. Maybe there was water, and all of these instruments that we're sending there are the things that are finding all of this out.
That's right. Yeah, narrowing down that history.
Yeah.
And looking and trying to answer the question of whether there is or was life on Mars. That's an important part.
All right. Well, understanding Mars and the different, rovers we've sent there to study that, you said you were part of the curation facility. So,
Yes.
And you said all the different things that are there, right? So you're talking about meteorites and moon rocks. Are there hints there that maybe can point towards the origin of life?
All right, so amongst the samples we have are samples of Mars. They come to us as meteorites. Here at NASA, we curate, we partner with the Smithsonian to curate the Antarctic meteorite collection. We have a very large number of meteorites from Antarctica. There is a team called ANSMET, the Antarctic Search for Meteorites, which goes every year and collects more of them. Actually, the team for that left into the field to go start their annual their search. I believe it was 2 days ago. They just started off.
All right.
So we get these meteorites every year, and they include periodically Martian meteorites. To date, not just the NASA collection, but all the collections in the world, we have on the order of, in excess of 1/4 metric ton of Mars meteorites.
Wow.
So we have samples of Mars that date back to billions of years old or as young as tens of millions of years old. We have samples that have come from evidently, only a meter deep to 10 meters deep or so, and others that solidified in place like a kilometer deep, much deeper than that. There's this random sampling from all over the planet. Here's where I say the thing that a lot of people don't like to hear, and that there's a wide range of opinion about in the scientific community on whether or not there's been life on Mars, is life on Mars. I'm fairly convinced by the meteorite evidence that there is not life on Mars, nor has there been, because in all those meteorites that we have from all over the surface, all manner of depths, all through a wide range of histories, this neat random sampling all over the planet, we have yet to see any evidence, any conclusive evidence of anything metabolizing in those rocks. And that tells us that not just today, but for a very long period through the past, that these meteorites have witnessed that nothing has lived in them. I think that's a fairly compelling result. It's not the final say, but
yeah.
There you go.
Because it's kind of interesting because you say Martian meteorites, but to an average Joe like me, I would ask the question: How does a piece of Mars get delivered to Earth?
Right. The solar system's a wild and woolly place with a lot of things that run into each other. Basically, take a look at Mars and you see impact craters all over it. What happens is, meteorite falls onto Mars or the moon or other asteroids, and they spall material off in an energetic, high-speed event known as an impact, and kick material clean off the planet, basically. And this stuff's, winds up in orbits that cross the Earth's orbit and fall to Earth, and we find them. Meteorites fall all the time. The reason why these guys, ANSMET goes to Antarctica, is because they tend to concentrate in places where they're easier to find. There are literally places in the Antarctic ice sheet where the only rock you'll see is something that fell there. And so they can go out and collect these things there. And that's the process. There's an impact at the beginning, a long period in the vacuum of space. They fall to Earth through a fireball, which destroys most of the meteorite, and anything survives, it winds up here.
All right. So Aaron, what would you be? Do you investigate the meteorites? Are you looking at organic compounds in them?
Yeah.
So what inside of them would sort of hint at life, that life would exist within that, and you can find traces of it?
So I actually usually look at it from the other perspective. So to me, I look at meteorites, which are the surviving remnants of likely asteroids, but potentially even comets. It's the material that falls to Earth. And so I look at that material and I start with the hypothesis that there was no biology. So this to me is, a dead rock from something that, was an uninhabitable environment. And then I'm looking at it for the chemistry that can go on without life present. And so for me, this is like the next best alternative to my time machine from earlier. Because now I have this asteroid that's been, floating around. It was formed at this about the same time that the Earth was forming in the solar system, so 4.5 billion years ago. And it's just been floating around in space, and every now and then pieces of these asteroids get fragmented off and they make their way in, to Earth, and then we get these samples. And then when I look at one of these samples in this 4.5 billion year old rock, and I find things like amino acids that are the building blocks of proteins, then I say, okay, so what was the chemistry that was going on in this asteroid or in the solar system 4.5 billion years ago that led me to find the amino acid glycine? That's kind of the perspective. And we know from sort of modern biology, there's DNA, RNA, and proteins. And in proteins in particular, there's 20 amino acids that are used in all of biology. And if you look at particularly amino acid rich meteorite, like the Murchison meteorite, which is probably one of the most famous carbon rich meteorites. So it's got about 80 different amino acids in it.
Whoa.
And many of them are not used in biology at all. And so, that's both a good indicator that it's not contamination from modern biology on it, but it's also indicative of sort of abiotic chemistry, happening 4.5 billion years ago, where there's a lot more random chemical reactions that are taking place, whereas in biology, everything is very controlled. You take a range of chemicals in that you eat, and then you turn them into a fixed number of chemicals that, make up your body.
Yeah.
Whereas abiotic chemistry will make all sorts of things, a whole range of things.
So what does that mean? That means that life here only has restrictions based on what could be possible, and then maybe there's amino acids that could create life maybe on another planet with a different set of amino acids that are not restricted by the norms of Earth. Is that kind of fair?
Yeah.
All right. I could be a scientist.
And
maybe not too fast. Okay.
Yeah. So there's two sort of variations on that. And both of them would sort of be the ideal case, or you can't have two ideal cases, can you? But both would be two very good cases.
Okay.
So one is that you're looking for life on another body, and you find life, and it uses entirely different amino acids. But it's got proteins, and they're just different than what we have on Earth. And you say, okay, cool. That's life, and it's not something that we just brought in our spacecraft.
Yeah.
The other difference that could happen is subtler. And it's an interesting thing. So we talked about carbon being able to make 4 bonds. And carbon makes sort of a tetrahedron shape when it's in these, when it's made 4 bonds. And so it's almost like a pyramid.
Oh, okay.
And so what's interesting is that the 4 atoms connected to that carbon atom, if they're arranged in a different way stereochemically, or so like the different sides of the pyramid, and then one point sort of floating up above it, you can actually have 2 different sort of chiralities or stereochemistries of those molecules. So we talk about it shorthand, left-handed and right-handed molecules,
okay,
which are really just an easier way for us to keep track of it. Your 2 hands are the same; they do the same job.
Yeah.
One's just a left hand and the other's a right hand, and you don't notice a problem until you grab the wrong glove, and it no longer fits on your hand.
Okay, so it's more of a fitting problem rather than like a dominant hand kind of problem. It's more of how things fit together.
Yeah, and when you measure the chemical and physical properties of molecules that are handed, they're identical except in how they interact with other handed molecules or certain kinds of light. And so if you found life on another planet that didn't use different amino acids, it would be interesting if it used a different handedness than life on Earth. So all life on Earth makes left-handed proteins, and all life on Earth, all.
What? Wow. Okay.
So all life on Earth uses left-handed amino acids in its proteins, and all life on Earth uses right-handed sugars in its DNA and RNA. And so if you were looking for life elsewhere and you found only right-handed proteins and say only left-handed sugars, then hey, you've got life, and it's definitely not Earth life. So it's, definitely a difference.
Yeah. So DNA RNA is a right-handed sugar that just happens to pair nicely with the left-handed amino acids, which are exclusive to Earth, right?
Yeah.
So
To biology.
to biology. Okay. So then is there a left-handed sugar of DNA RNA, or are you thinking there's something entirely different, like that would fit with the right-handed amino acid? Maybe I'm not asking the question right.
No, it's
It would still be DNA RNA?
yeah. So they're
Okay.
so DNA is deoxyribose nucleic acid, and RNA is ribose nucleic acid.
Right.
And what we leave out of there is a little prefix at the front that has a D. And in the case of amino acids and proteins, we leave out a little symbol in front that's an L. And so it's believed that one of those came first and was fixed. So you either had left-handed proteins or right-handed sugars that came about, and then proteins the other one evolved around it. So you started with a system that had left-handed proteins, and that fit really well with right-handed sugars, and that was where evolution took off, and that was how you got, sort of left-handed life and right-handed sugars.
I see.
But we were talking about synthetic biology and origins of life experiments. So I have left-handed proteins and right-handed sugars in me, and if you give me a drug that's made out of left-handed sugars, my left-handed proteins don't recognize those sugars anymore. And so those molecules can stick around a lot longer in my body because my natural mechanisms for processing, DNA from food I eat or, bacteria that are, floating around everywhere, they don't work on those molecules.
So what's an example of a left-handed sugar that would just sort of stick around?
So you could actually make just left-handed DNA and left-handed RNA.
How do you make it?
So that's a synthetic organic chemistry that ends up being fairly difficult. But what's interesting about this is, so people have gone in the lab and taken a naturally occurring left-handed protein, and they've synthesized the right-handed version of it.
Yeah.
And they found that it works just fine. It folds into its active state. There's no difference in the activity, except that now this right-handed protein recognizes a left-handed sugar molecule. So in this case, I think it was a glucose molecule.
Okay.
So we eat right-handed glucose all the time. That's what our natural food is. But this artificial enzyme that they made wouldn't recognize that. But when they gave it left-handed glucose, it did processed its chemical reaction just fine.
Huh. So then, all right, let's think about a hypothetical. So if you're on another planet that is in the mirror world, I guess, right? You got right-handed proteins and you got left-handed sugars. Would it kind of look, if it's like a mirror version of Earth, right? It's just like the same. Would that work? Or are we talking about something that would be entirely, like, things would just look different, act different, or is it just a mirror image?
It would be weight loss world.
Weight loss world?
You go there and eat all you want. You're not actually able to metabolize any of the food. Correct me if I'm wrong, but there's no reason why that sort of biology wouldn't work within its own system. But if we went there and tried to live there and eat the fruit off the tree or whatever, we wouldn't get anything out of it. If I'm not mistaken, there is a commercially available artificial sweetener that is the other-handed version of sugar, and it tastes sweet, but you can't digest it.
Huh. So what does it do? Does it make you? It's not weight loss city in that world, is it? Or is it because you're not processing it? Maybe you don't gain any weight. I don't know how that would work.
You can't use it.
You can't use it.
Yeah, it's just yeah.
So would you pass it then? It'll be okay. So it wouldn't just like stick around and be fat. Okay, that's good to know. All right, maybe I'll sprinkle that on some cupcakes or something and tell myself it's okay.
Yeah.
So that's interesting. Just the idea of right-handedness and left-handedness, and that there's a certain set of amino acids that exist on Earth, but there's a whole realm of possibilities that are that can exist just because we've studied, rocks in space or something.
Yeah.
So correct me if I'm wrong here, and because this is just a piece of trivia that I thought I knew, but now that you guys are here, I want to ask you: it's an asteroid when it's in space, it's a meteor when it's passing through the atmosphere, and a meteorite once it hits the ground?
Or a meteoroid in space, which is a smaller asteroid.
Oh, okay.
But yes, meteor when it's passing through the atmosphere, and that's the luminous ball, and then if anything survives to the ground, that's a meteorite.
Okay. Yeah, that's always something that's stuck in my mind, just because I used to call it the wrong thing, but then so when you study meteorites, you are specifically talking about the things that are on the ground. You're not going out and grabbing things and bringing them back, or you're not catching things as they're passing through the atmosphere. You're going out, and Antarctica is a good place to find them because black rocks on a white surface are pretty good, right?
Yep.
Is it fair to say meteors are falling through the atmosphere all the time?
All the time.
Yeah.
On average, there is a meteorite fall somewhere on Earth about once a day.
Wow.
But most of those are very small. You figure 70% of them are going to land in the ocean, because the planet's about 70% ocean. Of the remainder of the remaining 30%, half of them are going to happen during the day, and probably no one will notice them. Most of the ones that make it down of the remainder from that, excuse me, fall someplace it's difficult to recover, and it doesn't take much. Tall grass is enough, and you won't find them. Swamp is enough, you won't find them. If it lands on a nuclear power plant, you're not going to get those back either. On average, you get about a meteorite fall a day somewhere on Earth. There's the Meteoritical Society maintains a database of all the world's meteorites, and they record, give or take, about a dozen new meteorite falls per year. Those are the ones that are actually found. Some of those hit something and they become hard to miss, like coming through the roof of someone's house or a dentist's office. Yeah. Or other ones are just very large events that people go hunting for and find. Okay. So there's your statistics.
Yeah, and a lot of the material that comes in is just dust by the time it makes it through. And so if you think about like meteor showers that we have all the time, that's when Earth is passing through the debris from a tail of a comet.
Okay.
So this shooting star is material that's burning up, but some of that material falls in as dust, and so you would never, notice it.
Yeah.
But there's little grains of cosmic dust that are.
Yeah. We actually have a collection of that too, the cosmic dust collection.
How do you collect cosmic dust?
Airplanes, very, very high altitude. NASA operates a fleet of basically former spy planes, WB-57s here at Ellington, and ER-2, which is sort of like a U-2, out at Dryden, California, and they fly to 60,000 feet and up and deploy collectors that collect this falling dust out of the atmosphere.
Wow. So if it's not big enough to actually strike the Earth, you say it kind of disintegrates and doesn't hit the Earth, but it's there. It's in the atmosphere, just kind of floating around at 60,000 feet. That's cool. All right. I like to see that collection. That would be a pretty cool collection. Cosmic dust.
You can do that.
So once it passes through the atmosphere, is there a change that happens? Like, is there a difference with if you were to pick up a meteorite off the ground? Maybe there's something that the way it interacted with the Earth's atmosphere, or something that changed something that would be different from if you were to find the same thing up in space.
Yes. Okay. The most fundamental change is that a good probably 99% of it is now gone. It turned into a plasma on the way to the ground.
Oh, yeah.
So most of it's lost. Okay. The next big thing that happens is the outside of any meteorite you find is going to be covered with a molten crust. It's called a fusion crust. And it kind of looks like a pottery glaze. It's from basically flash melting the surface of the thing as it's coming through the atmosphere.
Wow.
And but probably the biggest change that happens to any of them, rule number one of meteorites is that they all have life, and they get the life from Earth. When they land here, they're coming into our biosphere. They will land on the ground somewhere. Even the ones in Antarctica, we found life in some life in a lot of these meteorites. Yeah. So that's the biggest change, because anything infecting these rocks tends to start to eat any of the carbon that's in there and process it and change like he was saying, it takes the native amino acids and starts to process them into, as you're basically turning it into microbial matter. Now it has a chiral preference as the microbes grow. They change it isotopically and chemically over time, and that's probably the single biggest change that happens, especially for organic chemistry and the things we're looking for these questions of origin of life and whatnot.
Yeah. So then how do you isolate to find out what things have not been affected and what things you can tell are within the meteorite that have, were there before it came to Earth and was affected by Earth's atmosphere?
Exactly the kind of chemical signals that Aaron was just talking about. Chirality, the amino acid abundance, looking for biomarkers / biosignatures, depending on what you want to call them, such as DNA. If you find terrestrial DNA and terrestrial microbes in this thing, then it's been altered. You can kind of expect that. But good laboratory practice is fundamental to sorting out exactly that question. You have your blanks and standards and replicate measurements and statistical analyses.
When I'm looking for molecules that are relevant to biology, I start with the assumption that anything that looks like biology in the sample is from biology that was introduced on Earth. And then I need the evidence in the meteorite to support that a conclusion other than that. So if the amino acids were made out in space, they should actually have an equal mixture of left-handed and right-handed amino acids. They shouldn't have that predominant, left-handed excess that biology shows. So if I take a bacteria and I run it through my meteorite processing methods, I'll get all L amino acids, and a little bit of it gets converted back to D during the process. So a meteorite, the initial, sort of baseline hypothesis is that if it's from the meteorite, it should be a 50-50 mixture. And if it's skewed towards left-handed, then I have to assume it's biological contamination, unless there's some other piece of evidence that tells me that, no, this really did actually happen out in space.
For example, way more right-handed amino acids, right?
So that would be, the kind of the ideal scenario, especially when looking for life. Yeah. There are other less sort of obvious markers that we can look at. So one of them has to do with stable isotope ratios. And so if we think about something like carbon, it normally has, in the most abundant form of carbon, has 6 protons and 6 neutrons, and it's carbon-12. Okay. And then about 1% of carbon on Earth is carbon-13. And then some trace amount is carbon-14, which is actually radioactive. And so that's what they use for radioactive dating. Okay. And so things that are found on Earth tend to be enriched in carbon-12 relative to carbon-13. And then even furthermore, things that are processed by biology on Earth really like carbon-12, and they don't like carbon-13 very much. Mm-hmm. Now, what's interesting is if you go out into a very cold environment, so out in sort of our pre-sun, our protosolar nebula, where places were much colder, you actually prefer the heavy isotopes. So carbon-13 is actually favored over carbon-12, more so relative to the preference on Earth. So it's not like you have 10 times as much carbon-13. It's like 1.01% carbon-13 instead of 1% carbon-13. Huh. And so from these very small signal differences, you can actually tell that something was actually made out in space rather than processed by biology on Earth. And it's these kind of subtle differences that they actually use in like Olympic events to determine whether people are using steroids.
Oh, really?
Because our biochemistry produces different, like testosterone, than like soy, plants, if you're getting it from plants. And so you can actually tell from the isotopic signatures whether the testosterone in an athlete came from them, or if it was produced in a lab or grown in a, some plant somewhere.
Wow, the answer's in the details. Yes. Literally, you're looking at the finest details, and even the slightest change, you can tell if it's otherworldly. That's pretty cool.
Yeah, and that's where you have to start with the hypothesis that this is contamination. Yeah. Unless you can prove that it's not.
Okay. So then, is there a effort to go out and, find something more pristine, maybe, rather than getting a meteorite? Maybe go out and get an asteroid that has not touched the Earth's atmosphere. Is there something we're doing now?
Yep. That would be OSIRIS-REx.
Okay.
So OSIRIS-REx mission is on its way to Bennu. It will collect samples from that asteroid. It is a carbonaceous body. We can tell this by spectroscopy at a distance. And actually, what we're touching on here is sample return missions and why you would want to do them. This is actually a really nice conversation leading up to it. For example, let me explain why you want to do missions like this in general. Let me use the example of Mars. Okay, we're seriously talking about starting doing this, collecting samples from Mars and returning them from Earth now. I had said earlier that we already have 1/4 metric ton of Martian meteorites on Earth. So if you're just going to go get more for the sake of getting more, it's really not a really good use of your resources. But we also talked about how any meteorite that falls to Earth is you have to assume it's contaminated. And so the really nice things you get out of a sample return mission that you can't get from meteorites is you get to collect materials where you to great detail know their contamination and alteration history. And by and large, you're going to get stuff that's very minimally altered. If it's that's usually one of the design goals of the mission. Definitely a part of the ones we've ever done. So you control the contamination history of the meteorite, and you get to know to great detail what it is, by monitoring during the course of the mission. You also get to select your samples. For the example of Mars samples, what we can do is collect types of rock that we don't have in the Martian meteorite collection. Sedimentary rocks take very poorly to getting pounded by a meteorite and blasted off the planet. They tend to turn into dust and you never see them. But we can go and carefully collect these. Basically, the meteorites that survive the trip from Mars to Earth tend to be very, very tough rocks. Now we can go and carefully collect the ones that we are actually more interested in some respects, for investigating the hypothesis of past or present life on that planet. The sedimentary rocks, the evaporites, the very friable, crumbly stuff that may preserve evidence of ancient organics. Those we can collect. Finally, you get to know exactly where your rock came from. When you look at a meteorite, most meteorites, Martian meteorites, we can say, where's this from? Well, it's from Mars, somewhere on the planet. If you go and do a sample return mission, you know the contamination history, you get to select samples that you don't otherwise have access to, and you know exactly where it came from on the planet. And you can take everything you learn about it in the lab and apply it to, an outcrop, a spot, a crater, a lithology, some location on that planet, and start to build the greater history of the planet in great detail that way. Right. So that, for whether it's for Mars or for Bennu or eventually comets or otherwise, that's kind of the driving impetus for doing these sample return missions.
Hey, well, I'm going to stay optimistic and say if we explore some of these spots in the more pristine environment of Mars, I think we can maybe look for the origins of life that way.
Well, if there's as Mark was saying, the rocks that we get on Earth from meteorites are really hard, tough ones. And so, the chances of life living in a solidified lava flow, it's probably a little bit different than if you could actually get material that was in a location that we think was the bottom of a lake, say, where you would expect life to have existed, and perhaps get actually, trapped into that sedimentary material.
Yeah. That's true, because location, right?
Yes,
it's a fair argument. So like I said, there's a lot of discussion about this. Not all scientists are how do I put it? We're still discussing it.
More research is needed.
More research.
And scientists hate consensus.
Yeah, pretty much.
So then what's, you said Bennu is carbaceous? Is that the word?
Carbonaceous.
Carbonaceous, okay. Carbonaceous.
It is black as coal.
Black as coal, so it's full of carbon. Very interesting thing to observe. So what's OSIRIS-REx going to do? Is it going to land and bring something back, or is it just going to stay there? What's the mission like?
So Bennu is about a 0.5 kilometer wide asteroid. OSIRIS-REx launched in September of 2016.
Okay.
Rendezvous is going to be in 2018.
All right.
And actually, the spacecraft is going to orbit for about 1.5 years and carefully map out the surface of the asteroid to identify scientifically interesting regions that it can collect a sample from. And the scientifically interesting question will be counterbalanced by safety, because you can't, really endanger the spacecraft while you're trying to collect a sample.
Yeah. Ooh, that sharp mountain looks really, really
Yeah.
interesting.
It's more important that you get the sample back than that you choose the exact most scientifically interesting
Right.
place. And so after finding a suitable location, the spacecraft is going to go down, and it's got almost like a little reverse vacuum cleaner. So it's got a little touch and go sample acquisition mechanism that will actually contact the surface of the asteroid, and then it's got nitrogen gas that it will actually blow into that surface, and that will actually push the dust into the sample collector. Mm-hmm. And so, like I was saying, like a reverse vacuum cleaner, right?
Okay,
You're blowing the dirt.
Blowing it, yeah.
That works on a rather small body because gravity is much less of an issue there. So the mission requirement is to get at least 60 grams, and from experiments on Earth and under similar gravity conditions, they should be able to get several hundred grams or more that will then be tucked away into a sample return capsule that will make its way back to Earth and will land. I'm amazed that people can do this with orbital dynamics, but it will land in Utah.
Wow.
In the desert in September of 2023. And then these samples will be transported to a curation facility and processed, and then eventually made available to researchers all over the world who are interested in studying this material.
Oh, that is cool. Fire it out to space and land it in Utah. That's a target. That's quite a target practice right there. That's pretty cool. So I guess it's going to kind of be like the moon rocks that we have here and are, some of them have actually never been exposed to Earth's atmosphere, right? They've been sealed. Like, are we going to expect the same thing for OSIRIS-REx? It's going to be sealed away from Earth's atmosphere?
Some of the samples will be preserved for future research.
Okay.
I think the design of the capsule doesn't keep it entirely free of Earth's atmosphere, but
okay.
it's for what they're trying to do, for the mission goals, that was appropriate.
Yeah.
But yeah, definitely some will be preserved away for future generations, just like any of the other collections.
All right. That's a pretty cool mission.
Yeah. Looking forward to seeing that.
Yeah, 2023. That'll be a cool thing to watch it come back. So Aaron, since I have you here, I did kind of want to bring up DNA sequencing, just because that's such an interesting thing that happened on the International Space Station, literally sequencing DNA in real time. Can you kind of explain kind of what that project is all about?
Yeah. So this is a project that actually has sort of two goals.
Okay.
So one is crew health and human exploration, and then I have my sort of ulterior motive or goal, which is looking for life elsewhere in the solar system. So it's a nice marriage of two applications of the same technology.
Pretty cool marriage.
Yeah.
Looking for life outside the solar system and studying astronauts in space. Pretty cool pairing.
Yeah.
Yeah.
And so this tech, the DNA sequencing, we want to use it for crew health, to be able to do environmental monitoring. And so you want to look on the International Space Station, or ISS, for microbes, be able to identify them, to know if there's harmful organisms there. And then as we think about going beyond ISS, if you're going to send humans to Mars and they're going to go on a 3-year mission, if a crew member shows signs of an infection, we want to have a diagnostic capability to know, so if you cough up some phlegm, okay, what's in that phlegm? And then is that something that needs to be treated with an antibiotic, or is that something that your body will clear on its own? Be able to make informed decisions about that, because we're not going to be able to, do resupply missions, it'd be hard to, hit a moving target flying to Mars and catch up to it.
Yeah.
So we're trying to give that sort of in-flight, diagnostic capability with the DNA sequencing. And then when the humans get to Mars, I'd like them to be able to go out and dig up a sample and extract it and actually look for life that's present on Mars.
Wow. So sequencing DNA is kind of like, I'm trying to explain it in as layman terms as possible to wrap my brain around it, because it is pretty complicated stuff, but it's basically identifying. right?
Yeah.
It's so if you said, if they have a cough, they can do a sample and they know exactly what you're coughing up. They know the exact makeup, and then you can identify what kind of antibiotic you need to take because you know exactly what's inside your body.
Yeah. Yeah.
Okay.
So DNA, is like a language. It's got an alphabet. There's only 4 letters. There's A, G, C, and T. But all life on Earth uses that same alphabet, from the tiniest microbe to humans. And so it's sort of like books in a library, right? The books are all different because they have more letters or less letters that are arranged in different words. And so, analyzing, sequencing DNA is like taking a page out of that book and then searching for all the words on that page. And then if you had a computer that could process it, you could say, oh, that page came from, A Tale of Two Cities, or that page came from, this book.
All right.
Or that paragraph. And so the more of that page or paragraph, the better of a match you can get.
Yeah.
If you have a chapter of a book, then you can nail it down to discounting plagiarism. You can nail it down to a single book or, a single organism.
All right. That's pretty cool. Although, I mean, for alphabet of 4 letters, life is pretty diverse for such a tiny alphabet. And you're taking analogies from books, and I'm imagining the books, but 4 letters that can make all these different things. That's pretty astounding.
Yeah. Well, so a virus can have around 50,000 of these letters in its entire genome. So all the instructions that a virus needs to do to infect a cell and then get the cell to make more copies of it, all encapsulated in 50,000 letters. And then something like the microbe that virus might infect could have, several million of these letters, and then humans are about 2.5 billion of these letters.
Yeah.
Or 3 billion. And then there are certain plants that even have like tenfold more of these letters in their genome.
Yeah.
But it's it's pretty amazing that biology can do so much with a limited, the limited alphabet.
That's true. But thank goodness there's no word in the English language that's 10 million letters long. So that's that's pretty good. It'd be really hard to write Tale of Two Cities with. You probably get one word in, and still it'll be the biggest novel you've ever seen in your life.
Yeah. Well, an interesting thing about that is they're actually starting to switch to, or trying to develop DNA as a way to store information. So it's like a new data, like replacing solid state drives or spinning hard drives is to encapsulate things in DNA.
Whoa. All right. Well, it's got a lot of storage, right? Because you can
yeah.
you can fit it. Wow. Okay. That's difficult to wrap my mind around. I'm thinking about storing something in like a cell.
Can I talk about something else weird?
Yes,
too?
please.
No.
This is not the place for that.
But so, one of the interesting things that we've talked about life as we know it and the search for life, and then there's this concept of being able to identify life as you don't know it.
Whoa.
And so we've talked about, left-handed and right-handed proteins, and it'd be great if you could find right-handed proteins or amino acids that aren't on Earth, or, left-handed sugars or sugars that aren't on Earth.
Yeah.
And so that's one of the cool things for me about the DNA sequencer project, is the way that it sequences DNA is actually got these little tiny pores that are just big enough for a single strand of DNA to pass through.
Huh.
And when there's nothing in the pore, you get basically an open current. And then as the DNA molecule passes through it, it blocks that pore, and so the current is reduced. And the reduction in current tells you something about the sequence of DNA that's passing through it. So like AGCTA would have a different signal blocking than GACTA, for example.
Thanks.
And so it's an entirely electrochemical way of detecting this, and you can apply it to other molecules that we might not necessarily recognize as life. So
LMNOP.
Yes, that's exactly right. And so people are using this technology to sequence RNA, which is different than DNA.
Mm-hmm.
It differs in the sugar, so it's deoxyribose versus ribose. But in RNA, an interesting thing is that you have more than the A, G, C, and T Actually, RNA uses U instead of T. But in things like ribosomal RNA and transfer RNA, which are present in biology, extensive modification is made of the bases. So there's actually like 118 different letters that show up in RNA that people are figuring out how to actually characterize using this nanopore sequencing.
Wow.
And so I'm interested in, not just me, a number of people are looking at this, but making a more universal life detection mechanism. So, if you can do DNA, but now you don't need the deoxyribose, it can be any sugar in there. Or instead of the A, G, C, and T letters, if you can L, M, N, O, P, as Mark said.
Yeah. It'll just look for letters and then just see what pops up. Yeah.
Yeah. And so you lose some of the resolution, so maybe you won't know that it was an A. But if you start seeing a polymer of semi-repeating, signals or letters, at some point that starts to tell you there's information there.
Oh, wow.
And that's where it gets really deep, is that, probably, one of the most important biosignatures or biomarkers is information, right?
Yes.
You have to have instructions for how to do whatever it is that the organism is doing and a way to copy that information.
All right, I can think of like 100 different ways we can go and just go on a tangent and talk about all these crazy topics. It's amazing, but we do have to wrap up. So I kind of wanted to end on something like some of the guests I like to bring in and ask this question specifically because we're at the Johnson Space Center and it's human space flight. But for you guys, in the search for life, why, from your point of view, is human exploration so important to discovery, especially in the field of looking for the origins of life?
I can give my answer, sure.
Yeah.
Basically, humans have an innate need to explore. It's something written into, I think, most children. Unfortunately, I think a lot of adults tend to lose that over time, but it's there. We can explore with robots. I'll use some air quotes. You can't see them, but it's exploration. But in a sense, with a robot, you are exploring through a computer screen, and that's fine. You do learn. It is exploration, but it may not be. At what point is that no longer satisfactory? I'd answer that with a question. At what point do you just have to go there and see it yourself? There's technical arguments for why you want to send people. They are, I believe, much better in a field environment when you're investigating something. They can turn around data, they can come up with new ideas, they can process things, they can actually pick, you can get a whole lot more out of having somebody kneel down, pick up a rock, and turn it over in their hand than in some instances, and some of the data you get from rovers and landers and such. That's been my experience. But fundamentally, there's that innate drive to explore, and that's the question. When is watching all this through a computer screen going to be unsatisfactory?
I got to follow that up. So I would, echo the just the much more versatile skill set that a human has compared to a robot. Where a human can look out for several miles and walk and adjust its path in a pretty easy way, and not get stuck somewhere. So you can explore a lot more ground in a given time period. If you want to dig a hole, you can dig a deeper hole because you've got a shovel, and you just keep digging until you decide that it's easier for a human to make these decisions themselves than try to communicate all that to a robot. But I think, as Mark was saying, it comes back to that sort of innate curiosity. Where what's over the mountain, what's across the river, what's at the bottom of the ocean. We didn't know that these other places would be good or great or useful, but you kind of have to know. And so, going to Mars and or the moon and learning how to live on the moon or learning how to live on Mars, teaches you something about, how to live on Earth, how to travel in space, how to live on other planets, and then it serves as a stepping stone. Okay, well, what's, beyond Mars? what's beyond our solar system. You know, we're going to need to develop light speed travel and all that. But, you know, assuming that we're able to do those things, you know, it enables the next frontier, if you will.
Very cool. Guys, thanks so much for coming on today. This was a fascinating topic, and always at the end of these, I get so charged, especially when we end with like the why. I'm like, yes, let's do it. Let's go out and explore. So thanks so much for coming on and talking about life. Can't wait to follow it up with one of these weird tangents that we almost went on today, but thanks again, guys.
Yeah, no, our pleasure.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0G, and I feel
The
fine.
shuttle has cleared the tower.
Became a thief for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Houston, welcome to space.
Hey, thanks for sticking around. So today we talked with Dr. Aaron Burton and Dr. Mark Fries about life in the solar system, went on a couple awesome tangents and had some great conversations just about everything life in the universe and just kind of scratch the surface, really. We can do a bunch more episodes just on this topic alone, but if you cannot wait and need to know the stuff right now, both Aaron and Mark are part of the astromaterials group known as ARES here. You can go to ares.jsc.nasa.gov to learn all about the different initiatives just going on in astromaterials alone. And you can learn more about OSIRIS-REx there, and you can learn more about meteorites and curation, and even you can learn how to get your hands on a meteorite if you are dying to get your hands on and study the sample material yourself and maybe search for organic compounds. Otherwise, if you just want to focus on just OSIRIS-REx, go to nasa.gov/OSIRIS-REx. On social media, if you want to talk to us there is the Johnson Space Center accounts on Facebook, Twitter, and Instagram. Also, Astromaterials has their own NASA Ares on several different accounts. Otherwise, you can find them. It's NASA Astromaterials. If you want to use the hashtag AskNASA on any one of those platforms, any one of those pages, you can submit an idea. Just make sure to mention it's for Houston We Have a Podcast so we can find it and answer it in a later episode for you, or perhaps dedicate an entire episode to it. So this podcast was recorded on November 28th, 2017. Thanks to Alex Perryman, Tracy Calhoun, and Jenny Knotts. And thanks again to Dr. Aaron Burton and Dr. Mark Fries for coming on the show. We'll be back next week.